A battery cannot cut your power bill because a battery does not make electricity. It is a container. Every watt-hour that comes out of one went in from somewhere first. And if that somewhere was your wall socket, you already paid for it and then lost another 15 to 20% to inefficiency on the way through. Charge a battery from the grid and discharge it at home, and your bill goes up. That is arithmetic rather than opinion. So when a $79 marine battery goes viral with a claim attached about your electricity costs, the honest answer requires 3 separate calculations, and I have run all of them. One of them produces a real saving. It is smaller than you expect, and it arrives too late. By the end, you will know the exact figure, and the one thing this battery is genuinely worth buying for. Let us dive in. A short clip. A cheap battery from a shelf everybody has walked past 100 times, and a number about the power bill. You have seen the format, even if you have not seen this particular version of it. Somebody standing in a car park holding a battery, price tag visible, an inverter on the tailgate, and a claim about what this does to a monthly electricity bill. Sometimes there is a phrase about what the power company does not want you to know. Sometimes it is presented as a discovery. And the reason it spreads is that a great deal of it is true. The battery is real. You can walk into a store today and buy it. The price is real, and by the standards of energy storage, it is remarkably low. It genuinely powers things. Plug an inverter into it, and you get mains voltage out of a box that costs less than a tank of fuel, which is a legitimately impressive thing to watch happen on a workbench. More importantly, thousands of people are running these successfully right now. In vans, in boats, in travel trailers, in off-grid cabins. Read the reviews and you find somebody who bought 3 for a solar setup on a trailer and came back for more, and somebody else whose battery lasted 5 years before it needed replacing. The DIY solar community's own assessment is worth quoting because it is generous and precise. They call it the best value lead acid available to experiment with. That is not a true deep cycle design, not the best battery. The best value for the money, with a specific caveat attached. So this is not a scam product, and this video is not about exposing a fraud. Nobody is being cheated at the checkout. What is happening is a substitution, and it happens so smoothly that almost nobody notices it. There are 2 entirely separate questions here. Does this battery work? And does this battery save money? The first question has an easy answer, and the demonstration in the clip answers it convincingly, because the lights do come on. The second question is arithmetic, and nobody in a car park does arithmetic, which is fortunate, because all of it can be checked. Every number in this video is either printed on the battery, published in a standard, or measurable on a bench with a meter that costs $20. Group 29 DC, 12 volts, 114 amp hours, 845 marine cranking amps. Those are the numbers on the label, and the rest of the specification is worth having in front of you before any arithmetic happens. Reserve capacity of 210 minutes, weight between 55 and 61 pounds, depending on the exact production run, which is a genuine consideration because you will only want to move it once. Flooded lead acid construction, sold as maintenance-free, meaning the caps are not intended to be opened and you are not topping up water. And a free replacement warranty running 1 to 2 years depending on which line you buy. On price, one honest note and then I will leave it alone. The 29 DC currently lists closer to $130, and the smaller 24 DC at 101 amp hours sits around $100. $79 is a sale price, an older price, or a smaller group size. None of that changes a single calculation in this video, because the arithmetic scales cleanly, and I will show you how to run it on whatever you actually paid. Now the classification, which matters more than any number on that list. This is a marine hybrid. It is not a true deep cycle battery. Those are 2 different designs solving 2 opposite problems. A starting battery needs to deliver an enormous surge for a few seconds to turn an engine over, and it achieves that with many thin plates packed close together to maximize surface area. A true deep cycle battery needs to give up a large fraction of its energy, slowly and repeatedly, without disintegrating, and it does that with fewer, much thicker plates that can survive being drained and refilled hundreds of times. Thin plates for surge, thick plates for endurance. You cannot have both in the same box. A marine hybrid splits the difference. Because a boat genuinely needs both, you have to start the outboard, and then you have to run a trolling motor and a fish finder all afternoon. So the plates end up somewhere in the middle, and the battery performs both jobs acceptably and neither one excellently. The community says exactly this, in almost those words, and they say it while recommending the battery. Best value lead acid that is not a true deep cycle design. Both halves of that sentence are doing work. So the label promises 114 amp hours at 12 volts. The rest of this video is about what that actually delivers. Watt hours are amp hours times volts, and that is the whole conversion. 114 amp hours multiplied by 12 volts gives 1,368 watt hours. Round it to 1,368. That is a genuinely respectable number, and it is where every viral clip stops. It is also where the honest version of this video starts, because two separate reductions are about to be applied to it, and neither of them is controversial. The first reduction is depth of discharge. Lead-acid batteries are sized to 50% depth of discharge across the entire industry. That is not a manufacturer being cautious or an installer covering himself. Take a lead-acid battery below half, and you shorten its life sharply, and take it low repeatedly, and you shorten it dramatically. Every serious reference on the technology says the same thing, and it is why an off-grid installer quoting you a 20 kilowatt-hour lead-acid bank is quietly telling you that you have 10. So half of that battery is a structural reserve rather than capacity. It is there to be present, not to be spent. 1,368 halved gives 684 watt hours. Now put that against a house. The average American home consumes somewhere around 30,000 watt hours in a day, 30 kilowatt hours. Against that, a fully charged battery holding 684 watt hours covers roughly 2% of one day. Percentages are slippery, so let me convert it into objects instead. 684 watt hours will run a laptop for several evenings. It will keep a router, a modem, and a reasonable amount of LED lighting alive comfortably overnight. It will run a full-size refrigerator for something in the region of a couple of hours, depending entirely on the fridge and how often the door opens. Those are real, useful things. In a blackout, they are the difference between an inconvenient evening and a miserable one. Now, the other list. Anything with a heating element will empty this battery in minutes. A kettle draws around 1,500 watts. A toaster is similar. A hairdryer runs 1,800. A space heater is 1,500 and runs continuously rather than in bursts. 1,500 watts against 684 watt hours is about 27 minutes of runtime. In theory, if the battery could actually sustain that draw. It cannot. And the reason that theoretical number is optimistic is the second reduction, which is where a paper from 1897 comes in. In 1897, a German scientist named Wilhelm Puchert published a short paper on lead accumulators, and it explains why almost every battery specification you have ever read is optimistic. The title translates roughly as, "On the Dependence of Capacity on Discharge Current in Lead Accumulators." It ran in the Elektrotechnische Zeitschrift, and it is one of those results that seems wrong the first time somebody explains it. His finding was this: a lead-acid battery does not contain a fixed quantity of energy. The faster you draw from it, the less total energy it turns out to have. Not delivers more slowly, has less. Take one battery, discharge it gently, and measure what comes out. Take the identical battery, charge it fully, discharge it hard, and measure again. The second number is smaller. Not because the energy went somewhere else, but because a portion of it was never accessible at that rate in the first place. The mechanism is worth understanding, because it makes the whole thing intuitive rather than mysterious. The reaction inside a lead-acid battery happens at the surface of the plates, where sulfuric acid meets active material. But the plates are not smooth sheets. They are porous, riddled with microscopic channels, and most of the material that stores your energy sits inside those pores rather than on the outside. For that interior material to participate, acid has to diffuse into the pores and reaction products have to diffuse back out. Diffusion is slow, it takes time, and it cannot be hurried. Draw gently and the acid keeps up. The whole depth of the plate participates, and you get everything the battery has. Draw hard, and only the outer surface can react. The acid at the surface gets depleted faster than fresh acid can arrive, voltage sags, and the battery hits its cutoff while a substantial quantity of active material sitting deeper in the plate has not been touched at all. The battery reports empty, with energy still inside it, which is why the entire industry adopted a convention. And this is the part almost nobody knows. Manufacturers rate capacity at the 20-hour rate. That means a battery labeled 100 amp hours was measured by discharging it at 5 amps for 20 hours at controlled room temperature until it hit its cutoff voltage. 5 amps for 20 hours. That is the number on the sticker. It is a real measurement, honestly taken, under the gentlest conditions the standard permits. Puchert's law describes how far it falls as you pull harder, and it does so through an exponent. If that exponent were exactly 1, capacity would not change with discharge rate at all. In real batteries, it is always greater than 1. For lead acid, generally the exponent runs between about 1.1 and 1.3. For sealed AGM construction, it is at the gentle end, roughly 1.05 to 1.15. For gæld, 1,2 For flooded lead-acid batteries, it runs from 1.2 up to 1.6. Flooded is what this battery is. It sits in the worst performing category of the entire family for exactly this effect. One worked example from the technical literature makes the scale of it concrete. Take a 100 amp hour lead-acid battery, discharge it at a high rate, and apply the 50% depth of discharge rule from the last section. The genuinely usable capacity comes out around 33 amp hours, a third of the label. And there is one more multiplier stacked on top, which is temperature. Cold conditions remove another 10 to 50%, and in genuinely cold weather more than that. So the sticker is not lying to you. It is answering a question nobody in a car park thought to ask, which is, measured how? Somebody bought 2 of these, wired them in parallel, and posted the result on a solar forum. He was new to it and said so, which is worth mentioning because he did nothing careless and made no mistakes anybody in his position would not have made. He bought 2 Everstart Max 29 DC batteries, connected them in parallel for a combined rating of 244 amp hours, and hooked them to a 2000-watt pure sine wave inverter. Then he ran a 600-watt load and expected an hour. Look at how reasonable that expectation is on paper. 244 amp hours at 12 volts is nearly 3,000 watt-hours nominal. 600 watts drawn from 3 kilowatt hours ought to run for several hours, and even taking only half the capacity should give more than 2. Here is what actually happened. The pack started at 12.85 volts, which is a properly charged, rested lead-acid bank. Within a few minutes, it had dropped below 12.2. Shortly after that, it reached 11.8, and he stopped the test. Those voltages need reading properly, because on a lead-acid bank, they are not arbitrary numbers. 12.85 is full. 12.2 is already down around 50% state of charge, which is the floor you are not supposed to cross. 11.8, under load, is deep into territory that does real damage to the plates. He went from full to the bottom of his usable range in minutes, on a load he had every reason to think was modest. His own conclusion afterward, once he had gone looking, was that the battery's rating had been taken at 1 amp. Now run the arithmetic on his load, because that is the whole lesson of this section. 600 watts, drawn from a 12-volt bank, is 50 amps before you account for inverter losses. Add those, and it is closer to 55 or 60 amps leaving the batteries. His pack was rated at 244 amp hours on the 20-hour standard. 244 divided by 20 is about 12 amps. So the rating assumed 12 amps, and he was pulling 50. 4 times the rate, on flooded batteries, with a Pukert exponent sitting somewhere between 1.2 and 1.6. Pukert then did in that man's garage exactly what Pukert said it would do in 1897, and the pack delivered a fraction of what the label suggested. Nothing failed. Nobody was defrauded. 2 perfectly good batteries behaved precisely according to a 128-year-old paper, which gives you the single most useful reframe in this entire video, and it costs nothing to adopt. The question is never how many amp hours a battery has. The question is how many amps you intend to pull out of it, and for how long. A battery is not a generator, and everything confusing about this claim comes from that one substitution. A solar panel makes electricity. Photons arrive, and current comes out. A wind turbine makes electricity, taking energy from moving air. A diesel generator makes electricity, taking it from fuel. A battery makes nothing. It has never made anything, and no battery in the history of the technology has ever added a single watt-hour to the world. It is a container. Every watt-hour that comes out of one went into it first, from somewhere, and somebody paid for that somewhere. So follow the money through a battery charged from your wall socket. You plug in a charger. The utility meters every watt-hour going into that charger, and bills you for all of it at whatever your rate happens to be. That energy goes into the battery. Then some of it does not come back out. Lead-acid batteries return roughly 80 to 85% of the energy put into them. The rest is lost, some as heat during charging, some to internal resistance, some to the chemistry itself. That is a property of the technology, and not a defect in any particular unit. Lithium does considerably better at 95 to 98%, which is one of the quiet reasons it took over. So you buy a kilowatt hour, you store it. You get back about 800 watt-hours. Then you use that 800 watt-hours in your house, and it displaces 800 watt-hours you would otherwise have drawn from the grid. Add it up. You bought 1,000. You used 800. You threw away 200. Charging a battery from the wall and discharging it into your own house makes your bill go up by roughly the size of the losses every single time, on every tariff, without exception. That is arithmetic rather than opinion, and it is the single most important sentence in this video, which does not mean storage never saves money. It means storage saves money under specific conditions, and there are exactly 3 of them. The first is buying at one price and using at another. If electricity costs less at 3 in the morning than at 6 in the evening, then moving energy through time has value, and the battery is being paid for the shift rather than for the energy. The second is storing something you generated for free. If a solar panel made it and the alternative was letting it go to waste, then everything the battery returns is money you did not spend. The third is avoiding a loss you would otherwise take. A blackout has a cost, and if a battery prevents that cost, it has saved you money without touching your bill at all. Nothing else is on the list. There is no fourth condition, and no arrangement of a grid-charged battery that produces a saving on its own. So the honest way to answer the question in the title is to take those 3 conditions one at a time and put real numbers against them. The first one is where every viral claim points, so that is where we start. Time of use billing is the one arrangement where a battery earns money purely by moving energy through time. Not every utility offers it, and if yours does not, then this entire section is theoretical for you. Where it exists, the utility prices electricity by the hour rather than charging one flat rate. Overnight, when demand collapses and nobody wants the power, it is cheap. Through the late afternoon and evening, when everybody arrives home and switches things on at once, it is expensive. So you charge the battery at 3 in the morning and run your house off it at 7 in the evening. The energy is identical, only the price changed. Let us put real numbers to it. Start with the honest usable capacity, carrying forward everything from the last 3 sections. Nominal is 1,368 watt-hours. Halved for depth of discharge, that is 684. Then apply a realistic Pukert reduction for the loads a household actually runs through an inverter, plus inverter overhead itself. Call it 450 watt-hours, genuinely delivered per cycle. That is a fair figure, and if anything it is on the generous side for a flooded marine hybrid. Now the charging side, because you have to put more in than you take out. At 80% round-trip efficiency, getting 450 watt-hours out means putting about 560 in. Call it 0.56 kilowatt-hours. At an off-peak rate of 12 cents per kilowatt-hour, that input cost you about 7 cents. Then the discharge side. Those 450 watt-hours displace grid electricity at the peak rate. At 30 cents per kilowatt-hour, 0.45 kilowatt-hours is worth about 13.5 cents. 13.5 cents of value, 7 cents of cost. Your net gain is roughly 6.5 to 7 cents per cycle. Run that every single day, without missing one, without a holiday, without forgetting, for a full year. 365 cycles at 7 cents comes to about $25. $25 a year. Now the other side of the ledger, which nobody in a car park mentions, $79 for the battery. But a battery on its own does nothing at all, so you also need an inverter, and a decent pure sine inverter of useful size starts somewhere around $100. You need a proper lead-acid charger, which is 30 to 60. You need cable heavy enough to carry 50 amps without catching fire, plus lugs and a fuse. Realistically, you are $200 in before anything works. Payback on the battery alone, at $25 a year, is a little over 3 years. Payback on the whole system is closer to 8, and now the number that settles the entire question. Cycling a flooded marine hybrid to 50% depth of discharge every single day is hard use for that construction. It is not what those plates were designed for. A few hundred cycles before meaningful capacity loss is a realistic expectation rather than a pessimistic one. 300 cycles is under a year. 500 is about 16 months. So set the two timelines beside each other. The battery needs 3 years to pay for itself, and it has somewhere between 1 year and 18 months of daily deep cycling in it. It dies roughly twice over before it breaks even. Change one thing, make the input free, and the arithmetic moves. Put a solar panel on that battery instead of a wall charger, and the entire cost side of the last section disappears. You are no longer buying the energy that goes in. Nobody meters sunlight. Every watt-hour the battery hands back is a watt-hour you did not purchase from anybody. The round-trip losses still happen. They just stop mattering, because losing 20% of something free costs nothing. So run it again. 450 watt-hours delivered per day, displacing grid electricity at a flat rate of 30 cents per kilowatt-hour. That is about 13.5 cents a day. Every day for a year comes to roughly $49. Against a $79 battery, payback lands around a year and a half. That is a real improvement over the arbitrage case, and it is the configuration nearly every successful owner in those forum threads is actually running. Panel, controller, battery, inverter, in a van, or a trailer, or a cabin, where the alternative is no power at all. Now the complication, which is the same one that ended the last section. A flooded marine hybrid cycled to 50% every single day is unlikely to comfortably outlive a year-and-a-half payback. You are asking plates designed as a compromise to do the hardest job in the lead-acid world, daily without rest. So the realistic outcome is that the battery roughly breaks even on itself, while you still owe for the panel, the charge controller, the inverter, and the wiring, which is not a disaster. It is simply not a saving either. There is an exception, and it is worth understanding because it is how experienced people actually run these. Cycle it gently instead of deeply. Take 20 or 30% out rather than 50, and lead-acid lifespan improves substantially, not by a little, but by a large multiple, because shallow cycling is the single kindest thing you can do to those plates. A battery treated that way might give you 3 or 4 years instead of 1. The trade is obvious once you see it. Taking 200 watt-hours a day instead of 450 roughly halves your daily saving, down to around 6 cents or $22 a year. But the battery now survives long enough to collect it several times over. That is the trade every off-grid owner ends up making, usually after killing their first bank. So put the 3 scenarios side by side, because this is the honest state of things after 3 sections of arithmetic. Grid charged, on a flat rate. You lose money, always by the size of the round-trip losses. Grid charged, on time of use, about $25 a year against a battery that dies before collecting it. Solar charged, about $49 a year deeply cycled, or roughly half that cycled gently over a much longer life. One battery. In the best realistic case, somewhere between $20 and $50 a year on a household electricity bill that probably runs somewhere between $1,500 and $2,000, which is between 1 and 3%. $79 does not buy a power system. It buys a measuring instrument, and that turns out to be worth considerably more. Nobody can size an off-grid installation correctly without 3 numbers, and not one of the 3 can be looked up. They are specific to your house, your hardware, and your habits, and the only way to obtain them is to run a small system and pay attention. The first is what your loads actually draw. A refrigerator has a nameplate on the back, and that nameplate tells you almost nothing useful. What matters is the duty cycle, how often the compressor runs, for how long, in your kitchen, at your ambient temperature, with your household opening the door as often as it does. 2 identical fridges in 2 different houses consume noticeably different amounts of energy across a day. The only way to know your figure is to run one from a measured supply and watch it for 24 hours. The second is what your losses actually are. Every inverter has an idle draw. It consumes power simply by being switched on, waiting for something to happen, and that consumption continues all night whether you use anything or not. On a small system, it can be a startling fraction of your total. This number appears in nobody's spreadsheet. Every off-grid plan built by somebody who has never owned an inverter is missing it, and it is the single most common reason a system that looked fine on paper disappoints in practice. The third is how you behave. That one sounds soft, and it is the most important of the 3. Living inside a fixed energy budget changes what you do, and you cannot predict how until you have done it. Some people discover they can have their consumption without noticing. Others discover that one particular habit, a coffee machine, an electric blanket, a workshop tool dominates everything else, and they had no idea. You learn more about your own consumption in 1 week of running a small battery than in a month of reading. Now the comparison that makes the case. A full home battery system runs into 5 figures. The difference between one sized on measurement and one sized on guesswork is thousands of dollars in either direction. Guess high, and you buy capacity you never touch, sitting in your garage depreciating. Guess low, and you have a bank that browns out every November, which is worse, because you now own an expensive system that does not do the job, and the fix is buying more of it. $79 and a fortnight of paying attention removes that risk completely. It is the cheapest possible way to find out what a $10,000 decision should actually look like. And there is the third saving from earlier, which I said I would come back to and will keep brief. A charged battery covers a short outage. That is not a reduction in your bill, and it will never appear on one, but the value is real on the night it happens, and everybody who has sat through a long outage understands why. So the honest purchase here is not a power system. It is tuition. If you are buying one, buy it for what it can teach you, and set it up so that it actually teaches you something. If you want the full guide, the load survey, the meter setup, and the sizing arithmetic worked through step by step, we put together a complete walkthrough covering everything here and more. The link is in the description below. Start with what to buy alongside it, because a battery on its own measures nothing. You need a pure sine wave inverter, sized for the load you actually intend to run rather than the biggest number available for the money. Oversizing costs you twice, once at purchase, and again every hour through higher idle consumption. You need a proper lead-acid charger with the correct profile, or a solar charge controller if you are going that route, not a trickle charger from a discount bin. You need a battery monitor. This is the component people skip, and it is the one that makes the entire exercise worthwhile, a shunt-based meter that counts watt-hours in and watt-hours out, rather than a voltmeter, because voltage on a lead-acid battery under load tells you very little, and you need fusing and cable heavy enough for the current, which I will come back to. Now the test protocol, and it is 4 steps. Step 1. Charge the battery fully, and then let it rest for a few hours with nothing connected. A rested voltage reading is meaningful. A reading taken straight off the charger is not. Step 2. Run one real load at a time, with the meter recording, and log the watt hours delivered rather than the minutes elapsed. Minutes tell you a story about one particular load. Watt hours are transferable to every other calculation you will ever do. Step 3, and this is the interesting one. Repeat the same test at different draw rates. Run something small for a long time, then something large for a short time, and compare total watt hours delivered in each case. They will not match. The gentle test will deliver more total energy than the hard one. You have just demonstrated Puchert's law on your own bench, with your own hardware, 128 years after he published it. And more usefully, you now know the size of the effect for your specific battery, rather than for a textbook average. Step 4. Run your actual evening on it. Whatever you would genuinely want alive during an outage: lights, router, phone charging, the fridge, and see how far it gets before you hit your 50% floor. What those 4 steps hand you is 3 numbers that nobody could have told you. A real figure for usable watt hours at your loads, a real figure for your inverter's overhead across a night, and a real daily consumption for the things you actually care about keeping running. Then the sizing arithmetic falls out of it almost automatically. Take your measured evening consumption, multiply by the number of days you want to survive without sun or grid. Double it because of the 50% rule. That is your bank size, in watt hours, derived from measurement. Compare that number to whatever you would have guessed before you started. The gap between those two figures is what the $79 actually bought you. 5 rules. And these are the difference between somebody who gets 5 years out of one of these and somebody who gets 18 months. 1. Charging a flooded lead-acid battery produces hydrogen gas. That is not a rare event or a fault condition. It happens during normal charging, every time, because a portion of the current always goes into splitting water rather than into the chemistry you wanted. Hydrogen is explosive across a wide range of concentrations, and it collects at ceiling height. So the battery lives in a ventilated space, not a sealed box, not a cupboard, not a plastic tote with the lid on, and nothing that sparks goes near it, which includes switching a connection while current is flowing. 2. Fuse it at the battery. A lead-acid battery of this size can deliver several hundred amps into a dead short almost instantly. If a cable chafes through against a chassis, or somebody drops a spanner across the terminals, the current available is limited only by the resistance of the path. An unfused cable in that situation becomes a heating element. It will glow, it will melt its insulation, and it will start a fire. The fuse goes at the battery end, within a few inches of the positive terminal, because everything downstream of that point is what it is protecting. 3. It wants to live above 50%. Treat the bottom half as structure rather than capacity. Every deep discharge is life you will not get back, and unlike most kinds of wear, this one is not gradual and forgiving. A handful of very deep discharges will do more damage than months of gentle use. If you take one habit away from this video, make it that one. Fool. Match the charger to the chemistry and the temperature. A charger set for the wrong battery type either undercharges it, which leaves it slowly declining in a way you will not notice until capacity is gone, or overcharges it, which boils electrolyte away and accelerates everything else. Temperature matters too, because the correct charging voltage shifts with it. A charger with temperature compensation is worth the extra money on a battery living in a garage or outdoors. 5. Keep it upright, keep it clean, and check the terminals. There is sulfuric acid inside that case. Flooded construction means it is liquid, and while these are sold as maintenance-free, they are not sold as tip-over-proof. Corroded terminals are both a performance problem and a mess. Fuzzy white or blue-green deposits on the posts add resistance exactly where you can least afford it, and they get worse on their own. None of those 5 are exotic, and none of them require special equipment. They are simply the difference between a battery that dies young for reasons its owner never understood, and one that quietly does its job for years. So here is the direct answer to the question in the title. Charged from the grid on a flat rate, this battery cuts your power bill by nothing. It increases it slightly by the size of the round-trip losses. every single time you cycle it. On a time-of-use tariff, it earns you somewhere around $25 a year against a battery that will not survive long enough to collect it. Charged from solar, it saves you closer to $50 a year cycled deeply, or roughly half that cycled gently across a much longer life. Against a household electricity bill of $1,500 to $2,000, that is between 1 and 3% in the best realistic case from a single battery. Anybody promising more has not multiplied 114 by 12, and then halved the answer twice, none of which makes the battery a bad product. It is a decent piece of hardware at a fair price, and the people running these in vans and boats and cabins are getting exactly what they paid for. What it will not do is what the clip implies, because no battery can. Storage moves energy through time. It does not create any. And the genuinely useful thing you can buy for $79 is not a power system at all. It is a way to measure your own house, your real loads, your real losses, and your own behavior under a fixed budget before you make a decision with a comma in the price. Wilhelm Peuckert published The Reason the Sticker is Optimistic in 1897. The arithmetic has not moved an inch since, and it will not move for you either. If discovering the practical, unglamorous corners of engineering matters to you, subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found. We will be tracking all of it as it develops. Now I want a real number from somebody who has done this. If you have run one of these on a meter, tell me the usable watt hours you actually measured, and tell me what load you measured it at. Both figures, or neither means anything. I read every single comment,